So here I have a relatively smooth table. It's pretty smooth to the touch, but if I could zoom in really close, better than my 5-year-old phone can, then this smooth table is actually pretty bumpy. In reality, if you were to zoom in really close on any object, any surface, they actually have really small, tiny bumps and valleys, so little hills and valleys, which actually makes their surface rough on a really small scale. All objects have a rough surface, but different objects have a different amount of roughness. Some objects might have big hills and valleys so that they're so rough that they even feel rough to the touch, like sandpaper. Or an object could have really small bumps and valleys that they're not noticeable to the touch. So different objects, different materials, different surfaces have different amounts of roughness. So what if I've got two surfaces that are touching and rub them together? So let's say that this gray jaggedy line is the surface of a table, and the purple jaggedy line is the surface of a calculator laying on the table. So what if I slide the calculator on top of the table? As the calculator, the purple jaggedy surface, is sliding across the table, the bumps and valleys of the calculator are going to run into bumps and valleys on the table. And so as the calculator is moving across the table, the purple hills and valleys of the calculator's surface are going to run into the hills and valleys of the table's surface. So let's say as one bump is passing another bump, it's gonna be like, hey, check me out. And then the other bump is gonna be like, hey, I kinda like you. And so these bumps are going to catch on to each other. And they're not gonna wanna separate, right? The bumps on one surface are gonna get caught in the valleys on the other surface, and vice versa. And that's gonna wanna prevent the object from moving further. And so what that does is it creates a force opposing the motion of the object. That force is friction. So the force of friction is a force that opposes the motion of an object or an attempt at motion of an object. So if an object is touching a surface and it's moving relative to that surface, then there is going to be a force of friction that opposes the motion of that object. So friction to the object is like, no, I don't want you to move that way. So friction opposes the motion of an object. Force of friction points in the opposite direction to the motion of an object. Hopefully this hasn't been too rough so far. Hopefully it's been pretty smooth. Friction is a force. It's a type of force, the force of friction. So how do we represent friction? Well, friction would be written as F for force. Remember, all forces are labeled with the big letter F. But this isn't just any force, this is a specific force, this is friction. And so we need to give the force a name tag. So our name tag for the force of friction is going to be a little f. And now what are my units for the force of friction? I can't force anyone to answer my question, but this shouldn't be new to you. It's a Newton. All forces are measured in newtons, no matter what kind of a force it is. I'm going to tell you that there's actually two kinds of friction. There is static friction, and there is kinetic friction. Let's talk about kinetic friction first. Kinetic friction is friction when an object is moving. By the way, kinetic means moving. Kinetic friction is friction that an object feels when it's moving. And this kinetic friction is going to point in the opposite direction to the motion of the object. Okay, friction. I'm gonna try not to cause any friction between us. I don't want this to turn into a heated argument, but let's talk about friction. Here's my cool SMUD flashlight. Not a mud flashlight, not a flashlight I put in the mud, but a SMUD flashlight. No, this is not a sponsored video. I just got a free SMUD flashlight, and that's really cool. We said there's two types of friction, kinetic friction and static friction. Kinetic friction happens when something's moving. So, if I have this flashlight and I move it along a surface, it feels a force of friction. So the bumpy surface of the flashlight and the bumpy surface of the wood cause a force of friction on the flashlight. The force of friction, specifically kinetic friction, slows down the flashlight. The force of friction opposes the motion of the flashlight, and it wants the flashlight to slow down. Remember, we said the force of friction always points in the opposite direction up to the motion of the object. So if my flashlight's moving this way, which direction is the force of friction? Flashlight moves that way, so friction points in the opposite direction, friction's pointing that way. So what if I tilt my surface and I'm still moving the flashlight? Okay, so the flashlight was moving up that way. Which direction does the force of kinetic friction point? The force of friction is going to point in the opposite direction to the motion. So if the flashlight moves that way, then the friction is going to be in the opposite direction, or that way. So the force of friction is going to be parallel to the direction that the object is moving, right? The object's moving along this surface, but point in the opposite direction to the motion. Friction doesn't want the flashlight to move. Friction's like the mean parent who won't let you do what you want, but the flashlight is stubborn and it keeps doing what it wants, but friction's like, no, I keep making the flashlight move, but friction is constantly trying to make the flashlight slow down. Friction is opposing its motion, but my hand is what keeps the flashlight moving. So friction's kind of like your parents. If you want to do something your own way that your parents don't agree with. So let's say you don't want to clean your room. So you are going to just sit in your messy room and you're not going to clean it, but every day, all the time, your parents are going to be like, hey, clean your room, clean your room. I need your room to be clean. You need to clean your room. Clean your room! Clean your room! And that's basically like something moving in friction, right? Whenever something's moving, it wants to move in one direction, and friction, like your parents, is like, no, I don't want you to move in that direction. And it's constantly opposing the object moving in that direction, just like your parents constantly oppose you not wanting to clean your room. So can friction be vertical? Yeah, friction can be up and down. If my object is moving vertical, so let's say my object is moving upwards, well, which direction does friction point? Friction points downwards. The object moves upwards, friction points in the opposite direction, downwards. So this whole time we've been talking about kinetic friction because our objects are moving. What about static friction? So static for us means not moving. And so static friction occurs when an object is not moving, but it's trying to move. So it occurs when there is an attempt to move. So an object will feel static friction when the object is attempting to move, but it is still at rest, but hasn't moved yet. So if an object is at rest, it's not moving, that doesn't necessarily mean that it feels static friction. The object has to attempt to move to feel a static friction. So where do we get static friction from? How do you get friction when something's not moving? The key is that static friction is only a thing when something's trying to move. Right now, is this flashlight trying to move? No. It doesn't want to move anywhere. It's chill, just sitting there. Now, does the flashlight want to move? Yeah. Which way does the flashlight want to go? The flashlight wants to slide down that way, because gravity's pulling the flashlight down, and so the flashlight's like, ooh, I want to go that way. Gravity's like, come here, come here. The flashlight's like, I know, I'm trying, but I can't, because there's this thing called static friction that's not letting the flashlight slide down. So the flashlight is trying to move that way, it wants to move that way, but static friction is preventing it from doing so. And it's static friction because the object isn't moving yet. It's trying to move, but it's not moving. So this is an example where we have static friction, and static friction is going to point in the opposite direction to which the object is trying to move. So if the object's trying to move down the surface, then static friction is pointing up the surface, and that's what keeps it from sliding down. We represent the force of static friction by saying F for force. Sometimes you'll see small s and small f for static friction. Not San Francisco,
And don't put a F sub s with just a small s because that would be the spring force. So if you're specifying that it's static friction, use SF as the subscript.
And for kinetic friction, we can write big F with a small kf. Not force of Kool-Aid fingers, but force of kinetic friction.
Actually, you're good just putting F sub k for kinetic friction. It doesn't have to be kf.
Now, the most important thing to note about static and kinetic friction is that static friction is always bigger than kinetic friction. The force of static friction is always greater than the force of kinetic friction for the same object. When the object is not moving, but it's trying to move, it feels the force of static friction. And the maximum static friction force is always greater than the force of kinetic friction that the object will feel once it starts moving. So what this is saying is that friction is stronger when an object is trying to move, and then once it actually gets moving, the force of friction decreases. So once the object starts moving, static friction becomes kinetic friction. So if an object is stopped and then it starts moving, friction is going to go from static friction when the object wasn't moving to kinetic friction when the object starts moving. So once the object starts moving, it's going to feel a smaller force of friction because once it's moving, it feels only kinetic friction, which is always smaller than the static friction.
So, here we have no friction, here we have static friction, and here we have kinetic friction. So I said that static friction is always bigger than kinetic friction. That means the force of friction is going to be stronger, greater, while an object is not moving than when it starts moving. So it's harder to make an object move than it is to keep an object that's already moving in motion because the friction is smaller once the object is already moving. So you can relate it to your homework. It's really hard to sit down and start doing your homework, but once you're already doing your homework, you can keep going. You kind of built up this momentum and you can keep doing your homework once you've already started. But the hardest part is getting started. Same thing with friction. It's harder to make an object start moving than it is to keep an object that's already moving in motion. The object is trying to move down that way, but static friction is preventing it from doing so. What happens if I push it? When I gave the flashlight a little bit of a push, it was able to overcome static friction, which is stronger than kinetic friction, and start moving. And once it was already moving, static friction isn't acting on the flashlight anymore, only kinetic friction. So once it overcomes that static friction,
the static friction becomes kinetic friction.
Kinetic friction is a lot weaker than static friction.
And the object can keep sliding.
I'm sorry, but I have to give you an equation. The force of friction is equal to a funny looking letter times F sub n. F sub n, that should look pretty normal to you. That is the normal force. And this is a Greek letter that every cat knows how to say. This is the Greek letter mu, mu, that's how you say it, and it means coefficient of friction.
You can use this equation to solve for static or kinetic friction. So when you're using this equation to solve for static friction, then this is going to give you the maximum amount of static friction. This equation gives you the max static friction force. We'll talk about what that means.
Okay, I'm going to try to be efficient when talking about this coefficient of friction. The coefficient of friction, it tells you what two surfaces are touching, and it also tells you how much friction will be between two surfaces based on how rough they are. So mu, the coefficient of friction, is telling you about the surfaces. And it depends on both surfaces. So there's different amounts of friction depending on which surfaces are touching. So for instance, I don't know if you've ever walked on like ice or on like a freshly mopped floor, those surfaces are really slippery. So there's friction between the sole of your shoe and the surface that you're walking on. And when the ground is slippery, there's a lot less friction between your shoe and the ground. Whereas if you're walking on like gravel or like a dirt road or even like a paved road, there's like the surface is a lot more rough, so there's a lot more friction between that surface and the same shoe. So it's the same shoe in both cases, but because you're walking on different surfaces that have different amounts of roughness, there's different amounts of friction. So the surface matters.
Okay, I've got one more thing for you. And you're like, friction, I don't want to learn about this anymore. But Mew got this. Mew got this. Not you, but Mew. Okay, so the value of kinetic friction doesn't change.
If you know the normal force and the coefficient of kinetic friction, and you calculate the force of kinetic friction, that force of kinetic friction won't change, as long as the object is moving. No matter how fast or how slow it's moving, the friction doesn't depend on the speed.
So the thing about static friction is that, static friction can reach a certain maximum. So static friction is only going to oppose as much as it needs to. So right now, the object is not trying to move, so there's zero static friction. If I tilt the surface a little bit, the object's trying to move a little bit, so static friction is going to oppose a little bit. If I raise the surface more, the object is trying to slide down more. It wants to move more, so static friction is going to push back more until I reach a certain maximum where the object wants to move down a lot, and static friction is opposing at its maximum. Static friction reaches its maximum amount, and that is the maximum force that it can oppose with.
So when you use the friction equation to solve for static friction, you're solving for the maximum static friction force.
So when static friction is maxed out, that's the maximum static friction force. And so if the object tries to move any more, then the object will be able to overcome static friction.
So on your equation sheet, you can see the middle equation right there. It says the force of friction is less than or equal to mu times the normal force. And what that's really saying is that the force of static friction isn't always maxed out. So the right side would be like the maximum static friction force, but static friction doesn't always have to be maxed out. Static friction can actually be less than the maximum. But the right side of the equation is always true for kinetic friction. Kinetic friction is a constant value if the normal force and the coefficient don't change.
So right here, my static friction force is at its maximum. What that means is that static friction is opposing at its maximum. Static friction is pushing as hard as it can push up the surface so that this thing won't slide down. But static friction can't push any harder, it's already maxed out. So if I tilt this surface anymore, the object is going to be able to overcome static friction because static friction can't push any harder, but if I tilt it, the object wants to fall more, so it overcomes the maximum static friction and it's able to slide down, and then that becomes kinetic friction. So what things affect friction? The normal force affects friction. So if we're talking about friction between this flashlight and this chair, the normal force affects the amount of friction that they feel between them. So you can think of the normal force as like how much the objects are squished together. If I push down really hard on the flashlight, the surface of the chair is going to apply a really big normal force to the flashlight, right? To keep it from falling through. The more normal force there is, the more the objects are like squished together. The closer together their bumpy surfaces get,
the more their surfaces are caught together,
and the more opposition to motion there is because those objects are so squished together. So the more normal force there is, the more like squished together the objects are, the more friction there is. So what's a way I can get more normal force besides me pushing down? Well, I could grab something that's really heavy, like a brick. Ooh, the brick has a lot of mass. there's a much larger normal force on this brick, which means there's a lot more friction. And you can tell because it's a lot harder to push the brick sideways than it was to push the flashlight sideways. Ooh. So there's a lot more friction between this brick and the chair than between this flashlight and the chair, and that's because there's more normal force acting on the brick, so the brick and the chair are squished close together, and so there's more friction. And it doesn't matter if it's static or kinetic friction, both are affected by the same amount by the normal force.
So what this really means is that mass affects friction. The more mass you have, the more normal force you have, the more friction you have.
So in terms of static friction, there is a lot more static friction acting on this brick than on this flashlight. One is a lot heavier and one is a lot lighter. Because the brick feels a much greater normal force, it feels a lot more static friction, so it's a lot harder to overcome static friction and make the brick move than it is to overcome the small amount of static friction of the flashlight, because it's so light, and make it move. Okay, so now I brought back my old fence board. I want to talk about the other thing that affects friction. The types of surfaces that you have rubbing together affect friction. Different surfaces have different roughnesses, different textures, right? So different surfaces made out of different materials are going to affect the friction between two surfaces. So for instance, I have this wood board which is like pretty rough to the touch, like you can even see it, right? Like then I have this piece of sandpaper. I don't know if you've ever felt sandpaper,
but this one's pretty rough to the touch.
So you can even feel like the bumpy surface of the sandpaper, right? So I have a surface made of one type of material and a surface made of another type of material. And so when I rub them together, I get friction. Okay, what about my hand? My hand also has a roughness to it. It's a surface, but it's made out of a different material than sandpaper. My hand is not sandpaper, hopefully. And I can rub my hand along this wood, and I still feel that friction. But there's a different amount of friction between my hand and the wood than there was between the sandpaper and the wood. And that's because my hand and the sandpaper are made out of different things. So the amount of friction between the two surfaces is going to be different depending on which two surfaces are rubbing together. So the friction depends on both surfaces. So for instance, the friction between the sandpaper and this piece of wood that's really rough, and the friction between the same piece of sandpaper and this very, very smooth chair is also different because I'm rubbing the same sandpaper on two different surfaces, so we get different amounts of friction between the two surfaces. So they actually make sandpaper in different roughnesses. So for instance, this sandpaper is 120 grit and this sandpaper is 240 grit, and the grit is just telling you like, hey, how rough is this sandpaper? And so when you can use that sandpaper to smooth out wood. And so what you're really doing is you are using friction to smooth out wood. And so depending on how smooth you want your wood to be, you use sandpaper that's different roughnesses, which will give you different amounts of friction when you're sanding the wood. Does friction depend on surface area? So I have this box of noodles. Yay, noodles! Also, that's super weird. They're like long, flat noodles, and then these ones are like spirally on the box. I have a rectangular box. If I slide this across the table, there's friction. My question is, does the amount of friction depend on whether this surface is touching the table or this surface is touching the table, right? This surface has a smaller surface area than this side of the box. So, does the surface area affect friction? Well, so the box is stopped. I have to push to overcome static friction. Okay, if I tilt the box on this side, the box is stopped. I have to push to overcome static friction and get it to move.
Go try it right now. Find a box in your pantry and push it on different sides and see if you can feel a difference, depending on which side is touching the table.
So I didn't notice a difference in how hard it was to overcome static friction. So what that tells me is that it doesn't matter that if the box is this way,
this way, no matter what surface is touching the table, there's going to be the same amount of friction. So it turns out that the surface area doesn't matter. Like, if you're trying to push like a really heavy box, it doesn't matter what side of the box you have touching the ground. The amount of friction is going to be the same. What matters is the normal force, or the mass of the box. So if you have a heavy box with a lot of mass, there's going to be a lot of normal force, which means there's going to be a lot of friction. So it's going to be hard to move it. But it doesn't matter which side of the box is touching the floor. There's going to be the same amount of friction no matter what surface area is in contact with the ground or the floor or whatever. Also, I think I mentioned this earlier, but does the speed affect the amount of kinetic friction, right? Because if it's moving, it's kinetic friction. So if I push the box slowly versus really fast, did the speed affect the amount of friction? No, the speed doesn't matter. The only things that affect friction are the types of surfaces, so the coefficient of friction, and the normal force, which is, of course, dependent on the mass.